So we'll start the lecture now. Right, so this is lecture number 15. Yesterday we talked about some ideas to do with memory hierarchy. You may have some understanding of the cache now, and you may start to appreciate the fact that the information, the data transfer, sometimes is the bottleneck in terms of your execution speed for the code, rather than the flops or the floating point operations per second, or the machine cycles that your processor can do. So we'll proceed from there. So this is going to be one lecture before we jump into talking about programming parallelized codes in Fortran. So we'll talk a bit more about arithmetic in computers. Okay, I'll touch upon some ideas, some subtle ideas regarding arithmetic that can cause issues. Something to do with optimization. In the previous lecture, we talked about optimizations O1, O2, and O3. We'll go a bit deeper into that as to what, I mean, there are hundreds of things the optimizations do. In case you want to talk, you can go out. I mean, there's no constraint with not going out, but please don't talk in the class, it disturbs. So we'll talk a bit more about optimizations, O1, O2, O3, and what actually happens inside those optimizations. Just touch upon some ideas, and then in the second half of today's lecture, we'll start talking about parallel computing, and we'll talk about a very important law that will help us decide, or that will help us analyze as to how much of parallelization can help us with code speed up. Okay. In case you want to read more about optimization flags, there's a link here as well. That's the GCC optimization. So GCC is GNU compiler, GNU compilers. So G-Fortran is a part of GCC. So you can read more about the optimizations available here. But we'll talk about a few in today's lecture. So as I said, in case you want to talk, you can go out. Okay. Otherwise, I'll have to ask you to leave the class. Let us not get there. Thank you. Now, there is sometimes a problem with excess precision. Okay. So we have talked about precision. We said that floating point numbers have some precision, right? We are using 8 bytes to represent floating point numbers, which is the IEEE standard for double precision. So that uses 8 bytes, or 8 times 8, 64 bits to represent your floating point numbers, out of which 1 is for sign, 11 is for exponents, and the remaining 52 are for representing the mantissa. So we've talked about that. But actually the precision available in the registers, where the numbers are extracted from by the logic unit, the precision with registers is sometimes larger than the precision available in your memory or cache. So even if we have an 8 byte double precision float, when it's sitting inside the register, it will actually the number will be represented using higher precision, in a higher precision. Now the reason that is done is because you might want to do many things with the number, and since registers is a very small amount of memory, so why not have some larger precision there? Okay, if a number is being used for many operations and you have a larger precision, you can do a more accurate calculation, right? So just to utilize on that, registers can sometimes have larger precision. So what happens is that if you're doing many operations before you send the number back into the cache of the memory, then you can have a more accurate arithmetic. But it can have problems with reproducibility, because if my machine has a register which has higher precision than your machine's register, or the way your or some machine is working is that after a couple of calculations, it is sent back to the cache and brought back in. So when it's sent back to the cache, it was represented using higher precision, but now the precision is reduced to again 8 bytes, and that lower precision or the approximated number in 8 bytes is brought back into the register. So we'll have slightly different answer. We may have slightly different answer. Okay, so that can affect the reproducibility of codes depending on which machine you are running it on. So for that, there is actually a G-Fortran flag called float store. So what that does is, after every operation, it will compulsorily send back the number to the cache. Now that is not the best thing to do, because you are wasting on machine cycles, but that will result in a reproducible code. So if you just want to check whether that difference in the answer that you are getting could be because of this reason, then you can switch on this flag and then compare the results. Okay, so we have to also start thinking about these minute ideas to ensure that the codes, the results are reproducible. Because if you do many calculations, and if you have seen any algorithm that transfers information in time, like in mechanics, it happens that you start with some initial condition and then you calculate the solution after some time, like we do in weather prediction. For example, you have the weather for today and you want to predict the weather for after 5 days. So that's a transient simulation. You start with today's initial condition and then you predict what will happen after 1 microsecond, 2 microsecond, and you keep running the simulation until you reach 5 days. But you can imagine that if you're doing 1 million steps in a second and you have 5 days, so you have 1 million times 60 times 60 times 24 times 5. So you have a lot of time steps, and if there is a small amount of error in one time step, that error can potentially, it can grow with time, and that can result in a solution which is very different from some other solution where the errors were different to start with. Okay, so we have to be careful in that sense. But that does not really happen because of the algorithms that we have, where the error does not grow with time. Otherwise things will go out of bounds very soon. But this idea should be known to you. So I just wanted to touch upon this idea.
Is it same as truncation errors?
This idea?
Yes sir, like so it is like you are saying that for cache the precision is different and for the main memory it is different.
No, truncation error is to do with your idea of truncating a number.
Yes,
okay.
It is also related to the precision, that precision is
You can call it truncation because, see, if you have an exact representation or you have a higher order representation, let's say 16 byte representation, and you map that to an 8 byte representation, in some way you're truncating. But truncation error typically used for truncating some terms in a series. That has nothing to do with this idea. So this is the same as what we have discussed previously in terms of the IEEE standard. Just a recall on that. So in binary numbers, like here, you have a mantissa and an exponent. So mantissa will be a sequence of ones and zeros, 52 of those. So that will represent the precision of the number. An exponent is 2 to the power. Just a parallel to that is representation in binary, because that in decimal, that is something that is more intuitive for us, is a number 0 point something, and then you have an exponent after that. Similarly here, this is the same slide that we discussed last time. So this is what we have. So the number becomes this, the equivalent representation in decimal from this binary representation that the computer stores is this. Okay, so everything is in the powers of 2. So that results in the machine epsilon that we have talked previously. So if you look at the bottom of the slide, so we have 52 bits for the precision. So that means that if I go back and you look at this mantissa, this is 52, it has 52 digits that it can store. So the smallest one that you can have is 0.00000 and 1 in the end. That's the smallest number you can store. So basically you can store 2 to the minus 52th precision. That's the smallest number you can have. So that results in 2.2 into 10 to the power minus 16. So that is the machine epsilon that we've talked about. And we'll encounter this again and again when we deal with precision. Okay. Just worth recalling this idea. And also remember that if you multiply the number by, let's say, 1000, in this case the number is pi, you do not lose precision. Okay. Multiplying by 1000 will not result in a loss of precision. It's just that the decimal point has shifted. I mean, although the calculation happens in binary here, but the idea is that the precision of the number is those 52 digits that you can store. Right. So let's talk about relative errors and absolute errors, because we tend to compute them in scientific computing. So absolute error would be, let's say you have an exact solution which is z hat, and you're calculating some number using an algorithm in computer. So that's an approximate value which is z star. So the error will be z star minus z hat, and we usually take a mod, because the magnitude of error is what matters, not the sign of error. Whether it doesn't matter whether the estimate is larger or lesser than the exact value, it's how far it is from the exact value. So it's a mod that matters. So what we do is we tend to calculate the relative errors, which actually will help us identify the correct number of digits in the error. Okay, because if your actual solution is exact solution is very large, right, that, I mean, like in the previous slide we multiply by 1000, that only shifts the decimal. Okay. So what matters is the precision in the error, that the number you have. So we calculate relative errors, and depending on the relative error, so let's say relative error is 10 to the minus k, then that means you have k correct digits in your solution. So the error is 0.0001, then that means that your error, I mean, if your solution has 3 correct digits, and then 4 correct digits for in this case, and then after that it's all erroneous. Okay. So that will also help us. I mean, this is how we talk in terms of precision, not in terms of the absolute value, because that doesn't matter. I mean, if your actual number that you're dealing with is very small, it's of the order of 10 to the minus 8, then absolute error will always look very small. But that does not mean that the precision of the error that you are calculating, or the precision of the solution that you are calculating, is also very small. So you have to scale it or normalize it with the exact solution. So this again states the same idea, that EM is the machine epsilon that you have. FLX in this case is the floating point representation of a number x that you have. Now again there will be errors, because you are using 8 bytes to represent a number, and it may happen that you may not be able to exactly represent the number with 8 bytes. Even numbers like 1000 or so on, in binary they may result in a never ending binary number. So in that case you will sort of clip it to 8 bytes or 64 bits in terms of in the binary representation. So to remember that this representation, the representation FLX minus x divided by x, the relative error will be less than or equal to your machine epsilon that you have. So this is just a test of that. So in Python, if you take 1.0 and you add a very small number, in this case the number is slightly larger than machine epsilon. So machine epsilon is 2.2 into 10 by minus 16, and this is 3. So if you add this and then you print the value of y, that is 1 point, and then in the end you have a 2. Now if you subtract a 1 from it, you get machine epsilon. And the reason is because this 3 into 10 to the minus 16 is not representable. I mean, if you add it to 1, then the closest representation in binary was this one. So if you subtract a 1 now, because it approximated the number 1.0003 with this 1.0002, so you subtract a 1, you are left with that difference, which is the machine epsilon in this case. Another way to do it is if you add 1 into 10 to the minus 16 with the 1, like you have here, then the closest representation is actually 1, because if you round this 1 into 10 to the minus 16, that actually rounds to 0. So in that case, if you subtract a 1 from that again, and then you get a 0, exact 0. So if you check whether y is equal to 1, it says true. Okay. So this is important for us because in scientific computing we tend to add numbers or subtract numbers where one number may be much smaller or much larger than the other number. So we have to be careful about these ideas. Now many people may argue that you don't need 16 digits in a solution, 16 decimal digits. So why do we have such as 8 byte representation of numbers? And that is exactly because of the idea that I just talked about. Let's take an example here. So we have pi. Again, this is in Python, but just to demonstrate the idea quickly. So you have pi here, and what you do is you multiply pi by a very small number. So you get pi times 10 to the minus 10. But that's okay, you don't lose precision here, it just shifts the decimal in this case. But now you add 1 to it. So now what happens is it wants to represent the complete number. So since it can only have these 16 digits in this solution in precision, so it stores the number as this and then discards everything after a couple of digits in pi, because you have added a very small number to a very large number, or very small number to a comparatively large number. Now when you subtract 1 from z again, then you expect to get y back. But when you added 1 to y, you lost precision. So now whatever you get will have some rubbish after some number of decimal places, because that's just how it's representing in the computer. But otherwise, what you have is you have lost precision. You only have now 6 or 7 digits of precision left. And this is the actual reason that we have 8 byte representation in double, and that can have a significant effect. If you sometimes start with just a 4 byte representation, you may notice that the solutions can be quite different in your code. So again, it's worth checking if you are using in Fortran we tend to be explicit, but in Python sometimes it might take a lower or you can actually have higher order representations where you can have more accuracy if you want. So it's worth trying those ideas just to make sure that that is not resulting in something called catastrophic cancellation of nearly equal numbers. And in this case, if something like this is happening, it's worth figuring out that if you're adding a 1 and subtracting a 1 later, maybe you can do a plus minus 1 separately or deal with large number calculations separately and then add it to the small number rather than doing it in a mixed manner. Again, compiler optimizers will try to figure these things out. They'll try to, if you're doing many lots of arithmetic, try to figure out if it has some cancellation of large numbers happening. It will try to club them together and club the small numbers together just to make sure you can retain on some precision. But again, it's an idea worth knowing about. So as I said that optimizations are very useful. In fact, we saw it yesterday when we noticed that the runtime was reduced significantly by using optimization starting from 01 to 03. So there's a link here that you can have a look at to read more about optimizations, just to get an idea as to what happens inside them. So there's one that I just want to touch upon, that's called FGSC. It's a global common sub-expression elimination. So you can switch it on with a minus FGCSE flag, or it's included by default in O2 and O3 optimizations in Fortran. So let's look at an example here. So you have a do loop where you are calculating yi as 2 times xi times pi. Okay, so in this case, and we tend to do it. I mean, if we have a formula, then we'll evaluate that in a loop like this. But what's happening here is that in every execution of the loop, you are doing 2 multiplies. One is the first one, which is 2 times x, the other is xi times pi. So that's like 2 multiplications per execution of the loop. We can save on that by calculating 2 times pi just once and doing just 1 multiply inside the loop. Well, that saves on a lot of operations, right? If your array size is very large, you literally save on n operations here. So if GCSC flag will take care of that. It will try to figure out situations where you have something like this. It will evaluate a different variable I've just shown that with pi 2, but it will have another variable. It will calculate that 2 times pi separately first and then multiply that with xi inside the loop. So, this is something that machine code will look like. Your code may actually look like what it looks above. Okay. So, if you switch on this flag, it will try to look for these situations and save on some time with this optimization. Again, but this may result in different results. So, if you use the optimization versus not using the optimization, it may, because computer arithmetic, computer multiply is not commutative. So, that way is you are doing a 2 times pi, whereas earlier you were doing 2 times xi times pi. So, that will again result in that small error that may result because of that. But again, it's worth knowing about it. It does not matter too much, but it's again worth knowing about these ideas. And that's again because some rounding happens at every step. And this is another idea where these higher order registers help. So, as I told you that registers have a higher accuracy. So, if you have registers which have higher accuracy, it may happen that 2 times pi is sitting, if you are multiplying, doing many multiplications and you are representing that with a higher order representation, then you may have a result which is much closer to the result with the optimization. So, this is one reason where higher order representation in registers is useful. Yes. Another optimization which is available in code, that's available, well, I have not pushed it to the repository, but that was just the Newton's code. But the idea is that you have functions, right? So, there was a code, I might ask you to write it later. So, like with calculator square root, I mean we can calculate the roots of any function. So, for that you need function and the derivative of that. So, here what we have is we have fx, which is the function fx, and then we have fx prime, which is the derivative of fx. So, if you are calling these, if you want to evaluate these again and again, you may have a function which evaluates that. But that calling a function again and again, rather than, because it's a very simple function, fx is x squared minus 4 in this case, like we had in square root of 2. So, rather than calling a function which has an overhead involved with calling a function and then returning an answer, you can literally put fx equal to x square minus 4 in the code. Why have fx? It's a very simple function. Similarly for f prime. But again, we may use that idea for readability, because in that case you can just change the function however you want, and then the code will work. But if you hard code your program to deal with x squared minus 4 and the derivative as 2x, it's very difficult for you or somebody else to modify that quickly to work it with any kind of function. But again, there's a overhead involved. So, inlining is an idea where what the compiler does is it picks the code from the function and puts it wherever it is called. Okay. Again, you don't have to do it, the compiler does it, but when the machine code is constructed, prepared, it looks as if you had not called the function. The function was hard coded in the actual main program. So, that's called inlining. So, you can enable the inlining optimization, or with O3 automatically has this inlining in it. So, that can, if your function calls are too frequent or too many, then you can save on some time by inlining functions through this optimizer flag. Any questions? Now, from this discussion, you may have gotten an idea that what's the point of knowing about these things when you have flags available, or you have optimizers available in Fortran. We'll just have minus O3 and hope for the best. That is fine. I mean, it's always good to do that, but compiler is only smart enough. I mean, there are situations where you have to modify the algorithm completely. The compiler may not know how to modify the algorithm as such. It is just able to do things which it has been told about. So using, firstly, always remember that use profiling. Don't jump into optimizing code without even realizing how much time that part of the code is taking. It's worth knowing. As I told you yesterday, that if there's a part that is only taking 5% or 10% of the time, and you try to optimize it, then all you can save on is this 10%. But that 90% is still there, which is taking a lot of time, significant amount of time of the code. So if you have 100 minutes that have been taken and you only save on those 10 minutes, you reduce that 10 to 8 minutes, then you have only saved on 2 minutes in total out of 100. Okay, so it's worth doing some profiling through some tools or manual profiling, but just figure out what parts of the code are taking how much time. Only then jump into optimizing things. So let's look at an example here. This is matrix multiplication, so we do that a lot. So you have two matrices, A and B, that are multiplied to get C. So what we do is we split these matrices into blocks. So C is a large matrix, let's say it's 10,000 by 10,000, which is very large. So what you do is you break it into 4 blocks. So each block, like C11 is a block matrix. It's not just one number, but a block matrix. So that will have a size of 5,000 by 5,000. Okay, so you are representing that 10,000 by 10,000 matrix as 4 blocks. So if you write all these matrices in terms of blocks, then this formula works in the sense that the block C11 is equal to block A11 times B11 plus block A12 times B21. Okay, so this times this plus this times this, as if you are multiplying elements. Okay. I'm sure you've seen this idea somewhere during the course of your mathematics courses, but if not, then if you think about it, it will start making sense. So this is an algorithm modification. If you are doing that, I mean, the compiler cannot do it for you. I am breaking matrix multiplication into blocks. Now, why are we doing this? Can anybody guess what sort of a benefit this idea will have? Any guesses?
The matrix order is so large.
So matrix is large, yes. What was your answer?
Memory utilization.
Memory utilization, yes. So what can happen is that your small blocks can fit into the cache. The huge matrix that you have may not fit into the cache, but the small ones could. And then if you're multiplying A11 by B11, then they may be available in the cache, so all the multiplication can happen at once. So these ideas are worth understanding. So this can have a significant improvement if you choose the sizes of the number of blocks smartly by knowing how big your cache is and so on. But don't just jump into every time you have to do a matrix multiplication, you start doing this idea. Okay, just check whether your actual multiplication is too slow, or if you break into blocks, are you getting an improvement, or is it making things worse and so on. But how will that idea help if things can fit into the cache? The way it works is that let's say you are calculating, this is a general Cij, so let's say C11, which is, as we discussed, this is these two were multiplied by these two. But if you have brought A11 and B11, let's say you have brought them into the cache to multiply them, that's the first operation you're doing, A11 times B11. And the next you want to do is you want to multiply A12 by B21. But you see that A11 as a block is already sitting in the cache. Okay, so why not utilize that? So what we can do is we can calculate a part of C11 first. So C11 is equal to A11 times B11. We keep that. And then rather than doing A12 times B21, we use A11 as much as we can, because A11 will be used again, right, to calculate C12. So C12 is these two multiplied by these two. So A11 is needed again. So what you do is you bring in B12 and you calculate a part of C12. So you have already calculated a part of C11 and you calculate a part of C12. So that way is A11, which was sitting in the cache, that 5000 by 5000 has been utilized. Again, I mean, you cannot have that big a matrix sitting in the cache, but let us say if it was big enough, then you have modified, you have utilized that A11. Okay, and that can actually result in a good amount of improvement, because if you can utilize the matrix in, and this is something that your compiler cannot figure out. You have to figure it out yourself, how many blocks you have to, because that is something that you have to code into the algorithm. Is that clear? Another example is that we have shown you is of transpose of matrix. So let's look at this example. So you have yes.
But in the previous case, we had to store the intermediate results somewhere.
Yes, yes, yes.
So in that case, wouldn't it be like you have to transfer your result back to some memory location?
Well, again, that depends on how big your cache is. I'm just giving you an idea here. Okay? I'm not implementing that algorithm here, but yes, the result will also sit into the cache. But the idea was that A11 was retained in the cache rather than throwing it out completely and bringing new, because you'll have to bring in A11 again. Maybe your cache already is storing C11 or C12, and in addition to that, you have these matrices that you have to bring in and throw out. So ultimately, you have to think about maximizing the utilization of cache as much as possible. So here's an example of transpose of matrix. So you have a matrix A, and so B is a B transpose or B is equal to A transpose, whatever you want to say. So now you think about it. I mean, if you are doing accessing elements of a matrix, we said that if we access that by columns, that's more optimum as compared to accessing by rows. But here we cannot get rid of accessing one of these by column rows and or columns, because if you write B transpose it is equal to A, then you are so if you look at this case, so first you fix the value of J, so that way you are accessing the elements of B by columns, but then A has to be accessed by rows. Or if you try to switch the loops, then you will access A by columns, but then B will have to be accessed by rows. Okay, so whatever you do in this case, one of them will be accessed by rows, so it will have a large stride, and that will result in those cache concerns that we had discussed yesterday. So again, we can use the idea of blocks here. So if you have B equal to A transpose, you can write B in terms of blocks like this, and A is in terms of blocks. And when you apply the transpose operation to blocked matrix, you get something like this. So the transpose is applied to the blocks as well. Okay, so what that means is that B11 matrix is equal to A11 transpose. So again, if you bring in, if your cache can fit in these matrices, then you can initialize or you can set the elements like this, so you don't have to have a large stride every time. You just bring in the whole matrix into the cache and then work with it. So extra elements which are brought in into the cache will not have to be done. So that again helps in saving some time. So here's actually the code of how you do it. I'm not going to go into the details of this, so I'll let you figure it out during the break that I'll give you. So what we have done is the first one is actually the actual multiplication without doing the the actual transpose without using the idea of blocks. And in the second case, we have reordered the loops. So in the first case, if you look at it, we do columns from 1, so we go in strides, okay, and then we visit the individual. So basically, so you have lots of columns, and you have broken that into blocks like this. So first you are saying that you will fix the block, and then inside the block you will visit the different columns. That is what this first two do loops are doing, and then you are doing the same thing with the rows. You decide on fixing the block, and then you visit all the rows in the block. So that if you look at it, then this and this are responsible for deciding the block number, and the ones inside that are just visiting all the columns or rows in the block. But if you do it in this order, it's exactly the same way that you will do transpose by visiting each and every element. But if you reorder the loops, so in this case what we have done is we have taken the block ones outside, and the individual we have got the individual ones inside. So that will now treat these blocks separately. So that way is and it will not affect the result at all. Okay. So this helps you do it in. So I'll give you some time to think about it, and then you can, if you have questions, I can explain that further. Right. Another idea here that let's take an example that you have two matrices A and B. In one case you multiply them, and in the other case you are adding them. So let's look at how much you do the computational experiment. So what you see is that the CPU time taken for addition is 0.0068, and for multiplication is 2.38. So multiplication is much larger time, and that makes sense because you are doing more operations. If you think about it, in addition you have a total of n squared elements in C, so you are doing n squared additions, so that's n squared operations. But if you think about multiplication, you have n cubed operations here, because for each element of C to be calculated, you have n operations that are being carried out. So that results in an overall n cube algorithm. So what we are doing is we are actually calculating, after calculating the time, we are calculating the rate. Okay, so that rate is calculated as the number of flops divided by the time taken. So number of floating point operations divided by the time taken. So that gives us the flops, floating point operations per second. So what we notice is that as expected, the number of operations in multiplication is larger, but still the rate in multiplication is much larger. It's as if, like, when you do multiplication, your computer can perform more efficiently. It is doing 838 megaflops here as compared to 145 megaflops in addition. Okay, and that makes more sense because rather than calculating just the time, because the complexity of the algorithm is different. So you should calculate how many operations is your computer performing per unit time. So any guesses why is it that the multiplication is larger efficiency than addition? Is the situation clear? So multiplication is more work, addition is less work. Multiplication is n cubed amount of work, and addition is n squared amount of work. So definitely multiplication takes more time, that we notice that here. But if you divide your number of operations by the time taken, you see that actually the work done per unit time is much larger or faster in multiplication than addition. Well, again the same idea, cache. Okay. So when you're doing multiplication, you tend to use the numbers more frequently. Addition is you add two numbers, that's it. That's the only time you visit a number, you just add it to another number, done. But in multiplication, what you're doing is you are multiplying two numbers, but that number is being used again and again to do multiplication. So like one row by one column, the same row by another column, same row by another column. So what's happening is numbers are being used multiple times. So what's happening is that you are utilizing the number more frequently, and if the number is sitting in the cache, then the time, I mean overall the time or the rate appears to be much larger in that case. If you had to discard the number every time, like in addition you are discarding those numbers after a calculation, you don't need them anymore, then it will actually appear to be of a similar rate than addition. But if you utilize the numbers more sitting in the cache, you tend to see a larger, well, I won't say clock speed, but larger number of flops. So I think after all these discussions, we have impressed further upon you that memory access is very important idea. Okay. So just keep that in mind. And actually what we notice is that these benchmark codes which are used to compare supercomputers or fast machines, they tend to they tend to show the good picture. So what they do is these benchmarks are designed in such a way so that they are doing more operations, but they involve a small amount of memory or data transfer through memory. So that way you see that it's a very fast machine, but when you bring it and you start doing something more useful with it, you realize that it's actually much slower than it was claimed in the data sheet. That was because the benchmark that was used was not doing a lot of data transfer to and back from the cache into the RAM and so on. So just remember that if the data sheet of the processor says this much and you're not getting that many flops, it's okay. I mean, it's let's be. So that is the reason sometimes different benchmarks are used, and each benchmark has a different rate that it gives. Okay. So it's worth looking at different understanding how the benchmarks are also working, so that you can understand which one is going to be which kind of a benchmark problem is closer to the problem that you will be running on your machines. So this is not for general purpose laptops that you use for regular purposes, but if you buy a machine which is worth 5 or 10 lakhs or more, it's our workstation like that. So it's worth understanding what kind of an architecture you need, so that and the architecture will be sometimes have will in most cases have data sheets available with them with benchmark results. So it's worth understanding what those benchmarks are before jumping into buying something. So one machine may have a better performance on one benchmark than the other one, and the other one may be performing better in some other cases. So understand how the benchmark is working, and then you can optimize your shopping as well. Questions? Good. So let's get into parallel computing. I'm sure many of you have been waiting for this. Okay. Last year I got a feedback that parallel computing only started after half of the course was completed. Well, that's how it is. I mean, if I start with this without discussing anything else, then you will not understand many other things. Okay. So we had to go through all this preparation so that now we can go very quickly. But the ideas that we discuss are going to be intense and deep, but they will make more sense. Okay. So in this discussion in parallel computing, we'll be talking about some basic concepts. I'll talk about ideas of shared and distributed memories, which is very, very important, because this is what separates the idea of using OpenMP like directives versus MPI, and you'll be hearing that 100 times per lecture in the next many weeks. So OpenMP, which is based on shared memory parallelism, will be discussed in the next. Well, I'll start this discussion after the midterm. So I'll discuss about OpenMP for the first 5 to 6 lectures, and then MPI for the next few, before closing the course with some GPU based parallelism ideas and implementation of those GPU based ideas in machine learning mainly, because this is where GPUs are mostly used nowadays. But majority of the content is going to be on general purpose parallelization, which is happening on the CPU using OpenMP and MPI. So there's some books here. I'll let you explore that later and have a look at these books. I'll upload a few books on Google Drive as well, where there's a books folder. So have a look at those. So this is Moore's law. I think the first lecture was where we discussed earlier. So we said that Moore's law, which is a law given based on stats, says that the processor speed doubles every 18 months. Now that was true many years ago, but then once we reached a stage where we could only fit enough transistors without melting the CPU, so there was a deadlock there. So then people realized that no, there's only enough that we can fit on a given CPU. So let's start having many cores. So rather than having just one core, you put multiple cores, and then we realized that even that is enough. I mean, we cannot put any more cores into a motherboard. So let's have many motherboards, and then let them communicate with each other with a faster communication. So that resulted in a multi-core, multi-node architecture, where you have the supercomputers, where you'll see many racks filled with computers, and each computer is a huge motherboard with many CPUs, and each CPU has many cores. So they all are optimized to talk to each other effectively and so on. Moore's law still works in the sense that not the processor speed, the clock cycle doubles every 18 months, but the number of cores now doubles every 18 months. Number of cores that you see in the fastest or the average machine that you have in the top 500, you'll see that they are almost doubling after every 18 months. So Moore's law is still valid in a parallelized sense nowadays. So let's talk about shared memory. So shared memory suggests that the memory is shared. Now what kind of memory is shared? So when we say shared memory, as we discussed that we have a hierarchy of memory starting from registers, L1, L2, in some cases L3 as well. We had L3, we saw L3 was also available on this computer last time, and then we have the main memory. So when we say shared, main memory is definitely shared. So the RAM is shared amongst the different processes or processors. L3 cache is also shared. As we noticed yesterday, that L1 and L2 were not shared on my machine. In some cases earlier there was no L3, so L2 was shared and L1 was available to a given processor. Now that's useful because if you have access to the same memory, all of them, you're distributing the work, right? Parallelization is all about distributing work. So work means numbers that you're dealing with, let's say. So their numbers are sitting in a memory. So you say you have 4 processors. You say that processor 1 you handle this memory, processor 2 this part of the memory, processor 3 this part, processor 4 that part. It's much easier to deal with that. And then each processor needs to do many things with those numbers, and these numbers can then in turn sit inside the cache. Let's say L1 cache of processor 1 has some numbers which is being sent to the register of processor 1. So it's good to have this hierarchy where some memory is shared and some is utilized, some is available only to that processor. Okay. But when we say shared, that means that it's the main memory that is shared. One of the caches could also be shared as well. But that completely changes the way we parallelize things. Okay. So it's actually a way to differentiate the parallelization techniques. Now the other kind is called distributed memory. So in this case, there's no shared memory. So if processor 1 has some memory access, processor 2 will not have access to that memory. So if processor 1 wants to share information with processor 2, there is no way it can do rather apart from sending the information explicitly. So let's talk in shared memory. So you have a whole RAM which is shared. So if processor 1 changes some location in the memory, processor 2 can later use it for some other calculation. But if you have distributed memory, then there is no transfer of information or no sharing of information possible. Data has to be transferred explicitly between the processes, and that can actually result in decrease in speed. And actually programming codes which are based on distributed memory is also very complicated. Like MPI is much more complicated, as you will see, than OpenMP. I'll give you OpenMP codes in exam, but I will not give you to write a full MPI code in exam, because that actually is sometimes a job of a few days to figure out. So in the exam for MPI, I'll give you some boxes to fill, figuring out what commands to put there rather than writing a code from scratch. Okay. It's much harder distributed memory parallelism as compared to shared memory parallelism. So you just don't have to think about computing or the algorithm. You also have to think about processor 1 calculates a result, but now that result is required by processor 2. So after this calculation, it has to send the result to processor 2, and processor 2 has to receive the result and acknowledge. And then once it receives the result, it starts calculating something. And once it has done that, it has to send the information to processor 1 or processor 3, whatever. And then you may realize that there's so many processors talking to each other. After some time, it just is very mind-boggling that we just get confused as to how to transfer information. Algorithm actually seems trivial. It's the information transfer that confuses us. So distributed memory can be quite hard to understand. But again, if you're talking about the scales of supercomputers or clusters, I mean, there's only enough you can put on a motherboard. So you have to work with distributed memory if you want to deal with larger problems. So now you may think that distributed memory is like you have one machine and you have another machine through motherboards, and each motherboard has their own RAM, so that's distributed memory. That is not always the case. Okay, it may happen that even on a single machine, like you have a single machine with you, you can still have distributed memory on that. So let's think of different processes. So I have PowerPoint running on my machine. I also have, let's say, a Fortran code running in the background. I also have MS Word running. So they're all different processes, and each one of these, I'm sure they are using the memory, they're using some RAM. If you check in the taskbar, you can see that RAM usage of each process is given. Sometimes one process is taking a lot of RAM, so you tend to kill it if that's not required. So what the idea is that each process has access to some part in the memory, and that should not be shared. For the same idea that we had this segmentation fault earlier, when you tried to access a memory location that was not available in the program. If PowerPoint tries to access a memory location which is being used by a Fortran code, it may corrupt that, it may change the bits in that memory, and that will result in something unexpected in the Fortran code. So the OS, operating system, has to make sure that if a process is given some memory, it is not allowed to see beyond that on the computer. So even on a single machine, you can see different processes are running, and each process has a limited has its own memory space. So this is also like a distributed memory, even though the RAM physically looks the same, is the same, but it's being split into different parts depending on what the OS is allotted to it. Okay. And we'll also talk about GPU based parallelism. So GPU, in terms of the rate at which it can do per unit core, is much smaller, but GPUs were actually designed initially for doing lots and lots of simple calculations, so that you can show something on the screen. So animation, this 1 pixel has to be calculated, 1 pixel value. So those simple calculations, but a lot of those, depending on how big your screen is, could be done so that you can see a nice video at high frame rate. But later we realized that if you have these fancy cards on your laptops or desktops, GPU cards, that they can be utilized for some algorithms can actually work quite well with these GPU cards. So that way is the GPU NVIDIA did really well. If you look at NVIDIA share values, you can literally see when machine learning came. When you see the rates of NVIDIA shares, you think that maybe 2 years ago, if I had bought some NVIDIA shares, I would be very rich. Okay, and now it makes sense. I mean, NVIDIA is delivering hardware for almost every machine learning based hardware. But anyways, I mean, there's nothing you can do about it. But the point is that GPU is also going to be very useful in the future. But the kind of codes we are talking about, high performance scientific computing, they are mainly to do with linear algebra calculations, which is still widely used. I mean, the big clusters that the big supercomputers we talk about, they're all CPU based supercomputers, not GPU based. Okay. But we'll touch upon GPU based computing. The idea of dealing with GPUs is very different from CPUs. This is not a GPU based course in C. Is there any course in computer science which deals with GPUs particularly? No? Okay. So GPU based parallelism courses are completely different the way they start. The language also, if you have seen CUDA for example, it's extremely different in the way than OpenMP and MPI that we'll discuss. But we'll talk about something called OpenACC, which is very similar to OpenMP, but that can utilize GPUs. It's only one lecture that we'll talk about it, but the idea is if you understand OpenMP, if you have been through OpenMP in 6 or 7 lectures, you'll quickly start picking what is similar or analogous between OpenMP and OpenACC. So if you have a code available to you, you can quickly add in directives, or if you have OpenMP based parallelized code, you can quickly convert that to an OpenACC based parallelized code and make use of the GPU card that's available on your desktop or laptop and get something, some improvement out of it. Okay. Any questions? Next is hybrid. Well, that makes sense. If you have many CPU, many cores on the machine, it's an octa-core machine, let's say, and you also have a GPU, and for some reason you have 2 processors on your machine. So it's a dual processor motherboard. Let's say you have an Intel Xeon machine, which has 2 processors, and each socket has its own few cores, and then you also have a couple of mother GPU cards. That means that you are a rich person. But it also means that you can do a lot of, why don't you utilize all these together? So if you can utilize GPUs as well as CPUs as well as the multiple cores within each CPU, then your algorithm is amazing, right? Interestingly, there are not many algorithms because the way it works, those who understand OpenMP have been writing OpenMP code, those who understand MPI have been writing MPI codes in scientific computing especially, and those who understand GPUs, machine learning. I mean, machine learning people don't tend to write parallelized codes because they use standard libraries which automatically do it for them. But the idea is that the way computing has evolved traditionally, and that mechanical engineers wrote programs for parallelization because they had to solve fluid mechanics problems. So hybrid codes, availability of hybrid codes is very few. So if you can understand these ideas, all of them, and come up with codes which can utilize all levels of parallelism, then you can actually come up with something very new and very useful. So at that note, I will stop here, and we'll continue after 10 minutes. So it's 6:45, so we'll start at 6:55. In the meantime, do think about that block matrix transpose algorithm that I talked about. I'll upload these slides on Moodle for you to have a look at them. So see you in 10 minutes.